Hello friends, in the last lecture we have discussed about the boron based reducing agents. Continuing to that, we are going to discuss today the another part, second part of this lecture. What we have discussed in the last lecture is sodium borohydride, its applications and the mechanism. After that, we have discussed diborane, that is B2S6, its applications as a reducing agent. And in today's lecture, we have to discuss the mechanism of all these applications which we have discussed in the earlier lecture. After that, we will discuss about the derivative of borane, that is 9-BBN, 9-boro-bicyclo-331-1. It is the IUPAC nomenclature of 9-BBN. But before going to the mechanism of diborane, let us first discuss the uh, applications that we have discussed earlier in the last lecture. Let us recall these applications and quickly, and then we will go to the mechanism part. Yes, we have discussed about the sodium borohydride, that it reduces ketones and aldehyde and doesn't reduce ester and nitro group. All these example explains that aldehyde and keto groups are reduced, not NO2, not cyanide, does not reduce carbon-carbon double bond also. They are also, it is, one exception is there, that ester group is reduced to alcohol. This is the particular, and this is the mechanism we have discussed earlier in the last lecture. Yes, these are the examples again which explain that acidic group, that is carboxylic acid, COH group, as well as halogen, is not reduced by sodium borohydride, as it is a milder reducing agent. Similarly here, again these examples are self-explanatory. And in the last example, when sodium borohydride is treated with cerium trichloride, and when two functional groups are there, that is aldehyde and ketone, here ketonic group is reduced to alcohol, and which is conjugated with carbon-carbon double bond. However, the aldehyde group is not reduced in this case, that we have discussed earlier. Okay, just a minute. See here, this ketonic group is reduced to secondary alcohol, while this aldehyde group, which is a non-conjugated, is remain as it is. Okay. This is an example that along with aldehyde and ketone, acid chloride is also reduced to primary alcohol. Okay, after that we have discussed about the diborane as a reducing agent. Diborane reduces ketone to secondary alcohol, aldehyde to primary alcohol. It also reduces the epoxide ring. The ring opening reaction takes place, and where ring is open, and we get secondary alcohol. In this case, the ring opening is expressed from which side, it is also very important. Here in this case, as it is symmetrical, there is no issue of ring opening, whether it opens from which side. Here there is no issue. Okay. Yeah. Just in this example, see, COH group is reduced to secondary primary alcohol. Cyanide is reduced to CH2NH2. This amide is reduced to amine. Ester functional group is reduced to primary alcohol group. Okay. But to see in the case of ester, the rate of the reaction is very slow. Okay, now let us see the mechanism of how the ketone is converted into secondary alcohol. We already discussed it, but we are we'll see it in this short brief. See this is the boron BH3. It is electrophilic in nature, as the boron socket is not complete. Only 6 electrons are there in the outermost orbit, and oxygen being a lone pair of electron, having a lone pair of electron, it is electron rich. So it donates its lone pair to the boron, and the bond is formed between oxygen and boron, which is a coordinate bond. As oxygen donates its lone pair, now oxygen have the positive charge efficiency here, and this borate structure is formed. Now oxygen gain its lone pair by from these pi bonded electrons, which means the pi bonded electrons are open on the oxygen. And now what is the charge on carbon? Positive, deficient. And this hydride ion from the boron migrates to that carbonium ion. So C positive H negative CH bond is formed, and oxygen gain its lone pair. You see oxygen now lone pair here now. In this way, hydride ion transfer takes place. Similarly, now one boron molecule have the capacity to induce 3 molecules of ketone or aldehyde. So same type of reaction will take place. The second molecule of ketone will come here. In the first case, boron will donate, oxygen of the ketone molecule donates oxygen, means lone pair will be donated by the oxygen to the boron. Same type of mechanism will be repeated, and hydride ion transfer takes place. In this way, 3 molecules of ketone will be reduced, and finally, on hydrolysis, we will get this secondary alcohol. If I start from aldehyde, I will get the primary alcohol. Okay. Again, here some examples are given. See this one. Here it is acid, and NO2 two functional groups are there. Acid functional group is reduced to primary alcohol, while nitro remains as it is. It is a selective reagent which doesn't reduce NO2 to NH2. NO2 group remains as it is. Only the acidic group is reduced to primary alcohol. In the previous example, we have discussed about the ester. The ester remains as it is, and that slow reaction is there. But in various books also, in some cases, it is given that ester is not reduced by diborane. However, acidic group is reduced to primary alcohol. So this is the best example when you want particularly reduce acidic functional group to alcohol without disturbing ester. Then this diborane is there. Okay. See, this is the example of amide. I earlier told you that the amide functional group is converted to amine. So C double bond ONH is converted to CH2NH. That is, you can say it is a decarbonylation reaction also. Here, this is again amide functional group, and it is ester. Ester functional group is as it is. Only this amide is reduced to amine. C double bond O is reduced to CH2. This is the epoxide ring opening reaction. Here epoxide ring is open, and we get the secondary alcohol. Okay, so all this we have discussed in the earlier lecture. Today we are going to discuss the mechanism of this conversion, all the conversion. See, this is the conversion of carboxylic acid to primary alcohol, CH2OH. How it takes place, let us see. Okay, in the first case, this oxygen, in the first step, this oxygen having the lone pair of electron donates its lone pair to the boron, and the bond is formed between this oxygen and boron. What is the nature of bond? It is a coordinate bond. Oxygen boron bond is formed, which is a coordinate bond. Oxygen have the positive charge now because it loses its lone pair. Now, after formation of this borate complex, oxygen will gain its lone pair from this pi bond between carbon and oxygen, that is carbonyl group. In this way, oxygen gains its lone pair. But what about the carbon? Carbon will have the positive charge, means deficiency. This carbon will have the deficiency. So this hydride ion from the boron is transferred here, and the CH bond is formed. See, you can clearly see here that how the CH bond is formed. This is the newly formed CH bond, carbon and hydrogen bond, hydride ion transfer. Okay. After that, on hydrolysis, this part cleavage takes place, and we get RCH2A, that is primary alcohol. This way, acid is converted to primary alcohol. I'm repeating again. The first step, oxygen donates lone pair to the boron. Coordinate bond is formed. Oxygen have the deficiency. Then oxygen gain its lone pair, which is initially lost from the pi bond. Then carbonium ion formation. In the next step, the hydride ion transfer from borane takes place, and we get this borate complex, which on acid hydrolysis gives primary alcohol. Okay. Now let us have a look on the mechanism of nitrile reduction, that is C triple bond N to CH2NH2, cyanide to primary amine. Here C, this is C triple bond N, and this is CH2NH2. Cyanide is converted to amine. What happens in the first step? Boron nitrogen donates its lone pair to the boron. You can see here clearly. Okay. This is the coordinate bond. In case of carboxylic acid, or in case of ketone or aldehyde, oxygen donate to lone pair. Now, in case of this cyanide, nitrogen donates lone pair to the boron, and the coordinate bond is formed. Okay, so this complex is formed. Now, as usual, nitrogen will gain its lone pair from the pi bonded electron. When these pi bonded electrons are shifted on the nitrogen, what will be the charge on carbon? Positive, that is deficiency. And then hydride ion transfer takes place. Hydride ion transfer takes place here. Carbon hydrogen bond formation takes place. Okay, then we get hydride ion transfer from boron. We get this. Now, on hydrolysis, what will happen? On hydrolysis, the hydrogen goes to nitrogen, C, and OH attached to the boron. If you consider the ionization of water as H positive and OH negative, H positive goes to nitrogen and OH negative goes to boron, and we get this. Then nitrogen gain its lone pair, carbonium ion formation, and then hydride ion transfer to the carbon with carbon, you can say. See, this is carbon hydrogen bond is formed. After that, again hydrolysis. Again, same type of reaction will take place. We can say, if I consider the ionization of water as H positive and OH negative. H positive will goes to the nitrogen, OH negative will goes to the boron, and I will get this one. Again, nitrogen have the deficiency due to the formation of coordinate bond with hydrogen. Then this bond breaking from cleavage takes place. Nitrogen gain its lone pair. This part is removed as a byproduct, and this is our main product, that is primary amine. This way, cyanide is converted to primary amine. Let us see once again the mechanism. That in the first step, nitrogen donates lone pair to the boron. Bond is formed between nitrogen and boron. After that, hydride ion transfer to the carbon because pi bonded electrons are shifted on the nitrogen. After that, hydrolysis, addition of H positive and OH negative across nitrogen boron bond. After that, hydride ion transfer from the boron to the carbon, we get this one. And again on hydrolysis, again addition across nitrogen boron bond, and then bond cleavage between nitrogen and boron, and finally we get the primary amine. So in this way, cyanide is converted to primary amine. Okay, after that, let us discuss the mechanism of amide reduction by diborane. How the amide is converted to amine. Let us have a look on the mechanism. See, this is the amide functional group, and how it is converted to amine. In the first step, as usual, the boron oxygen bond formed. Oxygen donates lone pair to the boron, bond is formed, coordinate bond. After that, hydride ion transfer. This hydride goes to the carbon. The carbon, pi bond is open on the oxygen, and the carbon hydrogen bond formation takes place. This is the carbon hydrogen. And then hydrolysis. Hydrolysis, the bond is this H and OH added across this boron and oxygen, and then hydride ion transfer to the carbon, followed by the bond cleavage between this carbon and oxygen. And finally, we get the amine. What did we discuss earlier? The ketone aldehyde mechanism, as well as acid conversion to primary alcohol. In all these, conversion of cyanide to amine, and acid to primary amine, acid to primary alcohol, as well as amide to amine, we have discussed that every mechanism have the same aspect. The first is donation of lone pair from the oxygen to the boron or nitrogen to the boron, and followed by hydrolysis. Okay, that is interesting. Epoxide reduction by diborane. How the epoxide ring cleavage takes place, let us see. In the first step, oxygen donates lone pair to the boron as usual. The borate complex is formed. After that, the ring opening takes place because oxygen have the deficiency now, because oxygen donates lone pair to the boron. So this bond is open here. Oxygen gain its lone pair. And what is the charge on this carbon? Positive, deficiency. So the moment the positive charge is created here, the hydride ion transfer from the boron takes place here on the carbon. So the carbon hydrogen bond is formed. This happens simultaneously. Hydride ion transfer, this carbon hydrogen bond formation, this carbon, and the oxygen gain its lone pair. Let me clearly see here, and boron. Boron now have the two hydride ions only here. Okay, and then after that, see here, one thing is missing here. Actually, oxygen is here. Oxygen. No oxygen. Carbon, here oxygen and boron. As carbon, here oxygen and boron. Because this bond is open. So what is here now? Carbon oxygen. After that, oxygen boron. Okay. Then hydrolysis. This is converted to OH. And in this way, we get the secondary alcohol. Now, regarding the stereochemistry, just a minute, regarding the ring opening reaction, I want to tell you here that passing the question why the ring opening takes place from this side and not from this side. It is the example of unsymmetrical oxide. The reason is very simple. If I open this ring from this side, I get the secondary carbon ion, and if I open the ring from this side, I get the Sorry, it's tertiary carbon, right? And here I get the primary carbon. It is mostly tertiary. So the stability of carbonyl ion decide the variability. Yes. So we have discussed the mechanism of the boron now. Now let us have let us have a look on the derivative of BBM, derivative of boron, sorry, that is called as 9-BBM. It's a long form. Its IPS name is a 9-boromycyclone 331 and the function is same. It's the same as a boron, but the drawback of the diborane or boron is that it have the capacity to reduce the more than one function group, that is three functional group. But this 9-BBN or other derivatives of the boron, like hexyl boron or any other variety of borons, like diacetyl boron is there. These are selective. So selectivity is very important aspect. Means out of multifunctional group, if you want to reduce or to act, or in general you have to carry out the reaction on one functional group keeping other as it is, then the selectivity is very important aspect. So first see the applications of this. Here see this is a alkene moiety. Same alkene moiety is used in case of 9-BBN also. Here it is diborane is used as a reducing agent, where 9-BBN is used as a reducing agent. So here, as I told you that it have the capacity to reduce three molecules because BH3, three hydride ions are there. Borane, it is the dimer. Actually, borane is the electrophile, electrophilic in nature, BH3. How many hydride ions are there? Three hydride ions. And in 9-BBM, if you see the structure, I will show you it on the next slide. There is only one hydride ion at the boron, so it reduces only one hydride ion. Okay, so yes, and this is the well-known example that on treatment of this alkyl borane or triaryl borane with propionic acid or acetic acid, we get alkane. Means if you see the change in the reactant end product, the change is only that alkene is converted to alkane. We have carbon-carbon double bond is there. We have carbon-carbon single bond. It is nothing but just addition of hydride ion across carbon-carbon double bond. And alkene is converted to alkane. And here also, alkene is converted to alkane. Only addition of hydrogen H2 across carbon-carbon double bond takes place. Nothing is different. Only selectivity issue is there. Selectivity. Okay, this is the another example where also carbon-carbon double bond is reduced to alkane. Alkene is reduced to alkane with this borane, any of the borane reagent, either thiborane or 9-BBM. And again, what I want to say you again that NO2 is not reduced with the BBM. Nitrogen group remains as it is. Yes, it is very important. Alkenes are converted to alkanes and alkynes are partially reduced to alkene. What happens if I use rather reducing agents like platinum, H2 platinum or any other reducing agent? They reduces alkyne carbon-carbon triple bond to alkene and alkene in turn reduced to alkane. But if I want convert alkyne to alkene, then I want selective reducing agent and that 9-BBN can do. See here, this is carbon-carbon triple bond. With 9-BBN, there is addition of what is the function? The hydride ion donor. In case of boron also, in case of BH3 also, know that BH3 on ionization get converted into hydride ion. It will do because boron is electropositive, right? Charge on boron means as compared to boron, hydrogen is more electronegative. So such type of boron having positive charge. Okay. Same case is here. And this hydride ion and the boron part added across carbon-carbon double bond. So here also hydrogen and this boron part added across carbon-carbon double bond. After that, acetic acid or propionic acid, this boron part is replaced by hydrogen. And if you look to the reactant and if you compare it with the product, nothing is happened in the addition of two hydrogen across carbon-carbon bond. Pi bond takes place, and it is where prime is connected to alkene. And what is this beauty of this reaction? That stereochemistry, to see the stereochemistry, we get the cis alkene. It means both the hydrogens are added from the same side. There is no evidence of formation of a trans product. Only cis product is obtained. That is the beauty of this Boron reagent. Boron, diboron, or any other like 9-BB and dicyamine boron or hexyl boron also. Addition takes place across carbon bond with the stereo specific having the stereo chemistry. The same functions we have discussed that this carbon-carbon double bond, and if instead on the second case, in the subsequent part, instead of using propionic acid or acetic acid, if I use the hydrogen peroxide or sodium hydroxide, then we get the alcohol. And if you compare the reactant with the product, there is nothing happen. Only the addition of H and OH across carbon-carbon double bond takes place. H goes to the carbon, which possesses less number of hydrogen, and OH goes to the carbon, which possesses more number of hydrogen. In this way, we get the primary alcohol. It means if you directly compare reactant with the product, it is looking like that the water had been added to the carbon-carbon double bond. Water means HOH, H2O, H positive, OH negative are added across carbon-carbon double bond according to anti-Markovnikov rule. Okay, but if you see the mechanism of the reaction is a takes place via Markovnikov's rule because H and PH2 added across carbon-carbon double bond as per Markovnikov's rule, and then boron part is oxidized to OH. Then it is looking like that water had been added, H positive and OH negative ions had been added across carbon-carbon double bond of an alkene in the anti-Markovnikov's rule. So remember to add OH to the carbon which possesses less number of means less substituted. Simply OH group to the carbon, OH group goes to the carbon which possesses less number of carbon. Which carbon is less substituted. So see here, this carbon is more substituted, this carbon is less substituted. So addition takes place. OH goes to the carbon which possesses less, while hydrogen goes to the carbon which possesses more. Right. So this is all about the this boron containing reagents, 9-ppm and sodium borohydride and boron. Okay, thank you.